Hi, I'm Joel, co-leader of Project MarsWorks.
And I'm Max, the press officer for Project MarsWorks.
Project MarsWorks was formed in 2017, attending competitions at the ERC in 2019 and the ARC in 2022. Our most recent project design cycle started in 2022 at the ARC, and we've been working for 3 years on our Scarab-1 rover.
The Scarab-1 rover is a marvel at design and innovation from us at the University of Sheffield.
In 2017, the project was founded as Project MoonWorks. We looked to compete in the UK SEDS Lunar Rover competition. We came first for Best Innovation and second for Best Critical Design Review and Outreach.
In 2019, the team rebranded from Project MoonWorks to Project MarsWorks, and we made our first ever debut at the European Rover Challenge with 6 of the original MoonWorks members on board. Then COVID hit, and we didn't have access to our rover, so the team disbanded for the year. But we came back together in 2021 to make sure we could compete in the ARC 2022 competition.
In 2022, Project MarsWorks went to the ARC at the Istanbul Technical University. Scoring well in the autonomous navigation challenges, a team of 7 learnt a lot. What we learned at the ARC 2022 was absolutely invaluable, from both seeing the rover function as well as speaking to the many other teams that came to the Istanbul Technical University from around the world.
And here's a picture of our team. In our team of over 50 members, we have a strict selection process for our astronaut training plan. We're looking for high meeting attendance, consistent, thorough project contributions. We're looking for good problem-solving skills with the adaptability and the ability to stay calm under pressure.
Once selected, each astronaut will undergo thorough training from all of our sub-team leads. This training will involve workshops, lectures, and meetings to go over the assembly process, subsystem design, priming for operation, and most importantly, failure modes and troubleshooting techniques. This will allow every astronaut to understand the rover completely and be prepared for any situation when getting the rover ready for all the challenges at the ARC.
As you can see here, we meet weekly at the Higgs building in room F20, where we discuss, overview, and look at every possible solution as a team to make the Scarab-1 the best rover it can be.
This is the George Porter building. As you can see, we have battery storage on the left here and waste disposal on the right. Going through these doors, each member has to sign in and out to ensure safety. We share this building with many other CCA teams, student-led projects. As you can see here, we share this room with another robotics team. This is where we have access to 3D printers, electronics equipment, nuts and bolts, and general assembly of the rover. This is the iForge. This is where the manufacture and machining of all our parts happens. In here, we have access to pillar drills, water jet cutters, laser cutters, mini mills, and many power tools, as well as more 3D printers and soldering equipment. The mobility system of the Scarab-1 features 6 independently powered e-bike motors driving TPU printed wheels. These e-bike motors have been internally welded to ensure the freewheel bearing is closed. It employs a rocker bogie suspension system where rocker arms are connected to bogie links and balanced by a differential bar. This ensures all wheels maintain ground contact on uneven terrain while keeping the chassis level. The system uses tank steering to allow forward motion, reversing, and turning. With a total mass of 53 kilos and dimensions of 0.85 meters in width, 0.94 meters in length, and 0.5 meters in height, this design prioritizes stability and durability. Lightweight carbon fiber tubes and 3D printed PET-G connectors provide strength and keep weight low. Staggered wheel widths and over-wheel motor supports enhance stability and ensure the suspension is stable under a huge variety of scenarios. This robust design ensures reliable operation across challenging planetary surfaces, including steep gradients, craters, and large rocks, all to be expected when carrying out the ARC mission objectives. The Scarab-1's electronic system is powered by 7 GNB 7000 mAh LiPo batteries with a combined theoretical runtime of 2 hours under full load. Each battery weighs approximately 800 grams. Power is distributed through a Taro high current 480 amp power distribution board that supplies energy to the motors via the ESCs. Each ESC will be mounted to the chassis in an effective heat sink, and the entire chassis is connected to the system ground for a safe electrostatic discharge pathway. The electronics architecture employs an NVIDIA Jetson Nano as the master controller, supported by Metexis H743 Wing V3 flight controller and Arduino Mega boards as slave devices. The NVIDIA Jetson Nano provides 472 gigaflops of AI processing power with its quad-core CPU running at 1.43 GHz and a 128-core Maxwell GPU operating at 921 MHz. This enables real-time processing for autonomous navigation and sentence integration. The Metexis flight controller features an MCU running at 480 MHz with dual IMUs for precise motor control. It includes 7 URAT ports, CAN bus support, and integrated battery monitoring. This will be used in conjunction with the Jetson to control the speed of the rover. This is done via PWM signal control of our 6 ESCs to provide forward, reverse, and turn capability. To ensure modularity and ease of maintenance, the XT90 and XT60 connectors are used extensively for subsystem connections. Real-time battery monitoring provides critical data via telemetry to the ground station for operational safety. All supporting architecture, excluding the batteries, will come to just less than a kilogram. The combined theoretical runtime of the 7 batteries comes to a total of 2 hours, which gives us ample time to compete in even the longest mission in the ARC 2025. The Scarab 1's manipulation system includes a modular 6-degree of freedom robotic arm powered by BLDC motors with O-Drive S1 drivers. Each joint communicates via CAN bus for distributed control and easy maintenance. ROS2 integration with MoveIt2 enables real-time trajectory planning and inverse kinematics for precise operation. The ARM's custom-designed 64-to-1 roller wave gearbox delivers high torque at low cost while maintaining precision. At the end effector, Dynamixel actuators provide adaptable gripping capabilities with interchangeable fingertip modules. This modular design enhances maintainability and ensures adaptability for diverse mission tasks. This custom-made end effector outperformed the other design iterations in tests such as gripping and pulling, twisting and pushing. This ensures that the rover will be able to manipulate the environment around it and complete every task of the ARC 2025. For example, the pulling the water ice subsurface extractor and manipulating the panel for the collaboration mission. With a total reach of 1.2 meters and a foldaway height of around 50 centimeters, the total weight of the robotic arm is 12 kilos. The science payload features an auger drill sampling system mounted on the robotic arm to allow customizable sampling locations for optimal soil collection. The auger drill pulls samples through the sheath into a servo-controlled temporary sample box that discards the first 5 centimeters of soil to avoid contamination before depositing it into the dual science box. The auger drill can be seen here, pulling regolith up through the sheath, providing a sample. The use of the robotic arm allows multiple samples to be taken, ensuring a minimum of 5 grams of regolith is taken. Once collected, the soil is exposed to 465 nanometers blue light, which excites flavin adenine dinucleotide, FAD, a metabolic biomarker, causing autofluorescence at 530 nanometers. An onboard camera captures fluorescence data, which is processed using ImageJ software to quantify brightness and the area indicating microbial activity. Environmental sensors simultaneously measure CO2 levels, temperature, humidity, and soil moisture to contextualize microbial abundance. Off-board tests include light microscopy and advanced staining techniques. Living microbes are analyzed using viable dyes like SYTO9, while microfossils and their microbial life are visualized with DNA-binding dyes such as DAPI. These complementary onboard and off-board methods ensure that both metabolic activity and structural markers are thoroughly examined, providing insights into microbial life abundance and environmental factors influencing its presence. The science box has a total weight of 800 grams and has the dimensions of 10 by 10 by 20 centimeters. The auger drill system will be around 40 centimeters long and weigh 1.5 kilograms. The base station to rover communication system utilizes a TP-Link EAP-225 outdoor access point, providing dual-band Wi-Fi connectivity over distances of up to 300 meters at 5 gigahertz. The on-rover subsystem communication is handled via CAN bus, Ethernet, USB ROS serial protocols, and MaVROS MavLink frameworks. On the base station, a Qt-based GUI integrates with ROS Humble to centralize and visualize sensor data streams and enable teleoperation via joysticks or Xbox controllers. This robust setup ensures seamless data transfer during missions while maintaining real-time feedback, allowing streamlined exploration of the entire ARC, Mars, and Moon simulated environments. The total mass of this system architecture is included in the electronics system total mass. Allowing connectivity over distances of 300 meters ensures we will stay connected to the rover at all points when exploring the terrain provided by the ARC. The Scarab 1 combines RG rover firmware with ROS2 for hybrid navigation capabilities. The Matec flight controller manages low-level motor control, while ROS2 Nav2 handles high-level path planning, obstacle avoidance, and waypoint generation using global planners like A-Star and behavior trees. RTAB Map SLAM processes depth data from the RealSense D435i camera to create detailed maps for localization in unknown terrains. For manual control, the system operates in guided mode, taking velocity commands sent from the ground station via Wi-Fi. This architecture provides a balance between low-level reliability and high-level autonomy for diverse mission scenarios as shown in the software system flowchart.